Hey everybody, welcome back. Today we're going to be working through a beginner-friendly Linux incident response lab using a set of fictional logs. Now, the point of this lab is not to memorize a handful of commands, it's to see how one clue creates the next question and how several incomplete records can be connected into one explanation that the evidence actually supports. So what we're going to do is basically start with a monitoring alert, then follow the activity through the server, and finish up with what a response team would actually do next. Let's get into it. Now, the alert that we're having for this lab is basically just saying there was unusual activity detected on a Linux server. Now, that's enough to begin a review, but not necessarily enough to say that someone broke in. So instead of starting with the story and trying to look for evidence that fits it, what we're actually going to do is start with the records and then let them narrow down the possibilities. However, before any of those can mean much, though, we need to know what system we're looking at and where this exercise actually begins. Now, the system we're looking at is a fictional Ubuntu web server named WebProd01, and the activity takes place on July 18th, 2026. The company, accounts, addresses, and events for this entire lab were created for the training. So if you want to do this by yourself, take a look at the description and the comments below because when you come back to those, you can kind of click on the link, download this presentation, and then get the lab materials at the end of it. I think it's around slide 25. But if you watch the video, I'll explain which package to use first and kind of give you some more context for doing the lab. For now, though, we just need to turn this broad alert into a set of questions we can actually answer and kind of get into the flow of how we work these kinds of things. Now, our questions usually form a pretty natural chain. First, did anyone get access? And if so, through which account and resource? Then, what happened after that access? Did the session gain more privilege or create a way to keep running? Once we know the impact, what should the response look like? That gives us a route through the evidence, basically access, activity, and response. Now, what we're going to do is begin with access using only a couple of basic commands to find the relevant lines. When a command appears, I will not be reading the syntax out loud, okay? I will just tell you what we're looking for and then kind of give you this moment to look at the result and explain what has changed. Here, for example, the command is searching a file for matching text. The syntax is available on the screen if you kind of want to reproduce it, but our attention is mostly going to stay on the evidence that it returns. So, before searching for a specific event, we should probably know what evidence the lab actually gives us. This is the evidence set that we will be working with. We have the authentication and system logs, a reconstructed command history, the system scheduled tasks, a file timeline, and the recovered training artifact. We will not be opening everything at once. We will just be using each source as it becomes relevant. Now, since our first question is whether anyone gained access because of our alert, the authentication log is basically going to be the first file that we need. So let's get into it and take a look. When we start pulling out the logs and such for access, what we're going to focus on is pulling out the failed password events, as you can see here. There is basically one isolated failure earlier in the day, then much later, a different source tries several usernames and then fails against Maya, that account, about 5 times in a short span. The individual failures are not remarkable by themselves. What gives us a lead is that their concentration around the same source and account. That pattern normally deserves follow-up, but we should not, quietly fold the earlier address into it. The reason being that the earlier Oracle attempt is separate from the Maya activity by both source and time. It could be ordinary background scanning, but this lab does not necessarily give us enough to connect it to the later sequence or really justify that conclusion. So what we do is set it aside instead of forcing everything unfamiliar into one story. That later source, Maya's, still remains our focus because its attempts form a connected pattern. So within that pattern, the next useful distinction is going to be between guest usernames and accounts that might actually exist on the server. The authentication log marks Oracle, admin, and Ubuntu as invalid users. As you can see here, Maya and root are logged differently, which tells us that they are real accounts in this exercise. That makes the repeated attention on Maya more relevant than the discarded guesses, but it still does not necessarily prove access. To cross that line, we need to find an accepted authentication event. When we search for accepted logins, the earlier public key sessions appear first. They look consistent with routine activity, although a real response would still confirm that they were authorized, as you can kind of see. Later, two passwords login succeeds as Maya from the same source that produced the failed attempts. Now, the earlier pattern has an outcome, obviously. Repeated failures against a real account, followed shortly by accepted passwords from that same address. For this lab, that is enough to treat the Maya sessions as unauthorized. It is not enough to explain where the password might have came from. The records show that a valid password was accepted, right? But they don't show whether it was guessed, reused, phished, or stolen from somewhere else. Those are possible explanations, not necessarily findings. So the honest answer is that the initial credential stores still remains unknown. Now, we can still keep moving by filtering the authentication log to the address we have already connected to Maya. And then we can kind of see the surrounding sequence without unrelated events breaking it apart. In that filtered view, the order kind of becomes pretty clear. The source tests several names, concentrates on Maya, fails repeatedly, succeeds twice with Maya's password, and then eventually disconnects. The filter has not added evidence, it has just put the relevant evidence into order. Access is now established within the exercise, so now we can follow the session forward and ask what level of control it has reached. The next relevant authentication records show Maya requesting a bash shell through sudo, followed by a session opening as root. As you can see, that moves the activity beyond access to one user account. A root shell carries administrative control over the host, including configuration, files, software, and scheduled tasks. But the presence of sudo is not suspicious enough on its own. Its meaning depends on who used it, for what purpose, and what happened around it. Earlier, Jay Lee used sudo to check the Nginx service. That appears consistent with routine administration, though authorization would still be verified in a real environment. Maya's event is different because it opens a complete root shell immediately after the suspicious password access we just traced. So the tool is not the finding, the connected context is. At this point, the authentication log confirms the root session, but it can't show us everything typed inside of it. For that, we pick up the activity in the reconstructed command history. The history here begins with basic checks of the system and available privileges. It then enters the root shell already confirmed by the authentication log, downloads a hidden file, makes it executable, and changes the system schedule. That gives us a possible continuation of the session, not a conclusion we should accept by itself. This history combines activity reconstructed from the Maya and root shells, and shell history can be incomplete or altered. The strongest lead here is the reoccurring scheduled task because the server should have other records that either support it or contradict it. The new schedule is designed to launch the hidden file as root every 10 minutes. Once that entry exists, the interactive logging can end while the scheduled task remains. That is why it functions as persistence in this exercise. It creates a reoccurring way for the file to be launched without the original shell staying open. The history says the entry was added. Rather than repeat that claim, we can now check the server's actual schedule. All right, here the cron tab contains two expected maintenance jobs and one additional entry that launches the hidden system update file every 10 minutes as root. That independently supports the lead from the history. We now know the schedule was present, but chronologically still matters. Did the file appear before the schedule changed, or do the shell records fit that order? The file timeline answers that without relying on the history alone. The hidden file is written first. The cron tab changes next. Then the root and Maya history files update afterward as the shells close. Those times fit the same progression we have already followed from login to root to the download file to the recurring task. One question remains though about that task. Was it only configured or did cron later try to launch it? Syslog shows the normal algorithm maintenance job, followed by cron invoking system update at 2220 and again at 2230. As you can see, that confirms the scheduled command was launched twice. It does not prove the file completed successfully, and it does not reveal what happened after each launch. Process, network, or endpoint telemetry would be needed to answer that, and those sources are outside of this lab. Now, what we can do is still document exactly which recovered file we are referring to without running it. The SHA-256 value on screen is a fingerprint calculated from the file's exact contents. As you can see, it gives us a stable identifier for this artifact, lets us compare it with another collected copy, and helps show whether the contents change. None of that requires executing the file. With the artifact documented, every source in this lab now has contributed its part. We can finally assemble the full sequence once from beginning to end. One source tests several usernames and then focuses on repeated password attempts on Maya. Two password logins as Maya succeed. During the second session, Maya opens a root shell through sudo. The reconstructed history then points to a download file and a reoccurring root task. The cron tab and file timeline support those changes, and syslog shows cron invoking the scheduled command twice. That reconstruction does not come from any single line. It exists because the authentication, privilege, shell, file, schedule, and system records agree on the same progression. Now we can return to the questions that give the review its structure. The real account targeted was Maya, and the focus source is the address shown on screen. Password succeeds at 2215. The session opens root shell through sudo just after 2216. Persistence is added through a root cron entry that launches every 10 minutes, and syslog later records two invocations. The one answer the evidence does not provide is how Maya's password was obtained. So the findings are clear enough to act on, but the unresolved entry method also affects how that action should be ordered. Deleting the file and removing the cron line may feel like the fastest fix, but doing that first can alter evidence before it's preserved. It would also leave the most important open question untouched: how the account was compromised in the first place. Removing persistence closes one mechanism. It doesn't prove that the host is clean or prevent the same access path from being used again. The response, therefore, needs to protect the organization and protect the evidence at the same time. That means containing the activity first, right? Using the organization's procedures to isolate the host and end unauthorized access. So while the evidence is still available, preserve the relevant logs, volatile data, disk information, and other telemetry the situation calls for. Then investigate the entry method and scope. Secure Maya's account, rotate affected credentials, and look for related activity on other systems. Recovery comes after that. Remove the persistence, restore trusted configuration, and then rebuild from a known good image if the host's integrity can't necessarily be established. Basically, all of this to say your methods are contain, preserve, investigate, and recover. These are not for unrelated topics. Each step keeps the next one possible. Now, if you want to practice this process yourself, start with the Viewer Lab Kit. It contains the evidence, instructions, and worksheet without the solution. After you complete the lab, please feel free to use the Creator package to compare your reasoning with the answer key and additional presenter material. Both links are embedded directly on this slide in the downloadable presentation, so feel free to click on the link in the comments below or in the description below to get access to this presentation. Thank you guys for watching. The main skill in this lab is just not about finding one dramatic log line, all right? It was about letting each record narrow down the next question until several independent resources supported that same sequence. That habit, follow the evidence, keep assumptions separate, and preserve what you need later, is useful well beyond this one Linux exercise. So, if you would like more hands on cybersecurity labs, subscribe, like, share, please, and I'll see you guys in the next one.